So still on shear force and bending moment diagrams or expressions, shear force and bending moment. Still talking about that. So let's look at another example. Let's say we have, in this case, we have a concentrated load at the center, and this concentrated load supported at A and supported at B with a span is at the center. Let's use a span of, let's say, 6 meters. Span of 6 meters. So if this load is, let's say this is A and this is our B and this is our W, which is this W, let's call this W, which is 20 kilonewton. So this, okay, we can still draw, let's draw another line, make it faint. Okay, let's say here is, this point is, if this is 6 meters, if this is 6 meters, so this is 3 meters and this is 3 meters. So here we want to know reaction A and reaction B, because the beam is symmetrically loaded. Reaction A will be equal to reaction B and will be equal to W over 2, our load over 2, and it's equal to 20 over 2. So there's no need of wasting our time going to determine the reaction at A or B, because this load will be shared, since the perpendicular distance are equal from it is at the center. It is not eccentrically loaded, it is loaded at the center, symmetrically loaded. So it is going to be 20 over 2, which is 10 kilonewton. If we still take moment about B, we can find reaction A. This will be times 6 meters, reaction A times 6 meters minus 20 times the lever arm, which is 3 meters, is equal to 0. Here we have reaction A will be equal to, this going to this side will be equal to 60, because this times this is 60 over 6, because we divide both sides by 6. So here we have reaction A will be equal to 10 kilonewton. Likewise, if you still take moment about point A, you can find reaction B. You can also say reaction B is equal to 20 minus reaction A, and this will equal to 20 minus 10, which is equal to 10 kilonewton. So in this case, what we just need to do, our shear force diagram will be simple. From here, we know that the load is at the center, so, and our shear force is rectangular, so we'll have our 10 kilonewton going up. As it goes up, it will meet the 20 kilonewton at the center, and once it gets to the center, this 20 kilonewton will pull it down. So here we have 20 kilonewton up to point C. The difference is that the first 10 kilonewton moves up. This is 10 kilonewton positive plus, and this one is, because once it is 10 moving towards this side, it will meet this 20 kilonewton. 20 subtract from the 10 to give us a balance of 10 kilonewton. So I have 10 kilonewton but negative. This one is positive. So this is our shear force diagram. Our bending moment diagram is still will be to look similar like the first one, but the difference is that we'll have, instead of it, because initially in the first one we had up to 4 kilonewton, up to 2 kilonewton, and the rest went this way. So in this case, it is going to be at the center. So unlike that, what we're going to have is, we'll have up to this point and also equal up to this point. So what is our maximum bending moment diagram expression or value? Let's go to our expression. So our bending moment at the center, which is at maximum at the center is 3 meters. So let's find it. So for our expression here, we know that we can find bending moment at 1 meters, 2 meter, at 1 meter, 2 meters, 3 meters, and up to 5 meters. But since we are looking at we want to know the maximum bending moment at the center, so it is going to be reaction A times that point is at 3 meters, which is at the center, times 3 minus, we will have a lever arm at that 3. We don't have any, it doesn't have perpendicular distance we are considering here. So it is going to be times 3. So what we'll have here is, here we have, is going to be reaction A is 10. So we have 10 times 3, which is equal to 30 kilonewton meter. So here, maximum value of 30 kilonewton. Remember, we need to still calibrate this line. So what we'll have here is positive, which is 30 kilonewton meter. So that's the maximum bending moment. Bending moment at A will be 0, at C will be 0. How do we verify that? If we are considering at C or B, this is, we call this B. So if it's at B, it's going to be 0. At A, is going to be 0. How do we find that? Here, let's take a moment let's consider this point, bending moment at this point. So here we have our reaction A times our perpendicular distance is 6 minus, here the load is from here to here, it is going to be minus 20 times perpendicular distance is 3 times 3. So this will be equal to 10 times 6 minus 20 times 3. So this is equal to 60 minus 60, which is equal to 0. So bending moment at the support, bending moment at the support is equal to 0. So both at A. So bending moment BM at A and B will be equal to 0. So another example which we need to look at under shear force and the bending moment expression, we need to look at simply supported beam carrying a UDL. Simply supported beam carrying a UDL. Place a UDL on it. So the span is, take a span of, let's say, 4 meters, and then we also place a UDL on it. So here we have a UDL on this beam, and this is our A, this is our B. Then we have a load, let's say 15 kilonewton per meter, and here we have, let's say here is 4 meters the span. So what we need to do is to find our reaction A, our reaction B. So let's start with reaction A and reaction B. Since this load is uniformly distributed and the beam is symmetrically loaded, reaction A is equal to reaction B, and will still be equal to the total load divided by 2. And the total load is 15 times E spread, which is 4 meters over 2. So this will be equal to our reaction A is still equal to reaction B, and is equal to 60 over 2. 60 over 2, we have 30 kilonewton. So we can also find out by taking moment about B. Alternatively, let's say RA multiplied by its lever arm, which is reaction A, by 4, which is 4 RA, minus the load. Total load here is, our load is 15 kilonewton per meter. So 15 times A spread, which is 4. Then the moment is, it acts at the center, which is half of this, times 4 over 2 is equal to 0. So next thing we need to do is to take this to the other side. What we have here is 4 reaction A is equal to minus this, we cancel, we have 2 here. 2 by this is 30. 30 by 4. 30 by 4, we have 30 by 4, which is 120. If we take this to the other side, it's supposed to be plus. So divide both sides by 4, divide both sides by 4. Our reaction A will be equal to 120 divided by 4, which is 30 kilonewton. If we still take moment about A, we'll have reaction B, still going to be 4 reaction B, minus the same 15 times 4 by 4 over 2, and our reaction B will be equal to 120 over 4, which is still equal to 30 kilonewton. So the next thing we need to do here is to determine our shear force values. For our shear force value, we know that the reaction at A is 30 kilonewton. So we have this 30 kilonewton going upwards. So we have it going upwards. So if we have 30 kilonewton going upwards, then it will be counteracted by, we have the load. This load is acting downwards. The total magnitude of the load is 15 by 4, which is total of 60. So 60 minus, here we have this load will, because it is a UDL, it is going to be an inclined line. Instead of having a rectangular line, we'll have an inclined line. So we'll have a balance of 60 minus 30, which is still 30 negative. So at the extreme end here, we have 30 negative. So here we are going to have 30 kilonewton positive at this point. We have also 30 kilonewton negative at this point. So this is our B and this is our A. So this is our shear force diagram. So the next thing we consider is the bending moment. For our bending moment diagram, draw a line also, and this point we have A and we have B. So our bending moment at this point, since it is simply supported at A will be equal to, we have reaction A. The reaction A, this lever arm is 0. So at this point it is going to be 0 at A is equal to 0. At B, same with at B is equal to 0. Reaction B times 0, we have 0. Then at any point, let's say 1 meter from here, at 1 meter, consider at 1 meter, what we'll have here is our bending moment will be our reaction, which is 30 RA times 1 minus the load. Load at 1 meter is 115 multiplied by 1 multiplied by 1 over 2. We're considering at 1 meter. So what we'll have here is, we have 30, because reaction A is 30 minus 15. 15 times 15 divided by 2 is 7.5 or 7.5. So minus 15 over 2, and this will be equal to 30 minus 7.5. So that is our reaction at 1 meter. At 1 meter, a reaction at 1 meter, sorry, not reaction at 1 meter, bending moment at 1 meter, a BM at 1 meter. So will be 30 minus 7.5, and what we will have is 22.5 kilonewton meter. So at 2 meters, what we will have is our reaction times 2 meters, which is RA by 2 meters, minus the load, which is 15 times 2 times 2 over 1. So what we're going to have is 30 times 2 minus 15 times 2 times 2 over 2, not over 1, beg your pardon. So this will cancel this. So what we'll have here is 30 times 2 minus 30. This is equal to 30. At 2 meters, we have, which is at the center, the bending moment is 30 kilonewton meter. We consider at 3 meters, we have the reaction here times, because at 3 meters from here, from A, we have reaction times A minus our load here is 15 times 3 times 3 over 2. So what we have here is a reaction times 3, not 30, because we're talking about 3 meters. So we're going to have 90 minus, here we have this will give us 9 times 7.5, because these two can cancel out to give us 7.5 times 3 times 3. So what we will have is 7.5 times 9, which is equal to 67.5. So here we have 67.5. So what we have here is 67.5, 90 minus 67.5, which is equal to 22.5. So at 3 meters, our bending moment is equal to 22.5 kilonewton meter. So we'll consider at 4 meters, which is at the extreme end at B, which is where X is equal to 4 meters. So what do we have there? We have our reaction A multiplied by 4 minus 15 times 4 over 2. So these two, we cancel 2 from here. What we'll have here is, here we have 30 multiplied by 4. We have 30 multiplied by 4 minus, here we have 30, 15 times 2 is 30 times 4, which is 120. So we're going to have 120 minus 120, which is equal to 0. So we'll have that as 0. So our reaction, our bending moment at B, bending moment at B is equal to 0. So we can easily plot this. Let's plot it. So if we want to plot our bending moment diagram, or we want to plot it from what we've gotten so far, what we need to do is, we have the first point at A. We said that A is 0, so we have 0 here. At the second point, we were considering at 1 meter, at 2 meters, at 3 meters. So at 1, at 2, at 2 meters, at 3 meters, and at 4 meters. So here we have 22.5. Here the second one we got 30. At the third point we got 22.5. So if we join this, what we're going to have is we're going to have our bending moment in this form. It is going to be in a curve form, a parabolic form. So we'll have something of this nature with the maximum bending moment occurring at 2, which is here, the maximum bending moment at 2. So we'll join our lines. So this is parabolic. We'll have something of this nature. So the maximum bending moment is at this point, which is 2 meters. So at 2 meters. So we've been able to label this as our bending moment diagram. Bending moment diagram. These are shear force diagram, and this is our bending moment diagram.